Let's consider now weak acids. These are acids that do not dissociate 100%, and so they form an equilibrium when dissolved in solution. So we have this following reaction, an acid with water, and then we'll have an equilibrium. So we have a forward and reverse reaction, and the acid will donate a proton to water, and then what will be left is A minus. So we have an equilibrium occurring here. So we can use the techniques that we learned from the last chapter in equilibrium to calculate the concentrations of each species at equilibrium. So we have an equilibrium constant you've seen, as we call it K sub A for acid, and it's just the concentration of the products divided by the concentration of the reactants. And since water is a pure liquid, we leave it out of the equilibrium constant. And so we can solve for the equilibrium concentration of each of these three species. And since we solve for the concentration of H3O+, we can find the pH of the solution, since the pH is just the negative log of the H3O+ concentration. So let's do an example. Say we have acetic acid, and acetic acid is what's in vinegar. So vinegar is basically a 5% solution of acetic acid in water. And so acetic acid has a Ka value of 1.8 times 10 to the minus fifth. So we have our acid reaction. And since it has an equilibrium constant value, then we have an equilibrium, and acetic acid is a weak acid. And we can write the equilibrium constant. Now remember, this A stands for a molecular formula. So acetic acid, has carbon, hydrogen, and oxygen in it. So I'm just letting A stand for the part of the acid besides this hydrogen that's donated. Okay, so now we use our techniques of equilibrium. We need to define an extent of reaction. And for these weak acids and bases, it's usually the most convenient to let X be the amount of H3O+ that has been formed in the reaction. Then the concentration of A minus is also X, because there's a 1-to-1 ratio between H3O+ and A minus. And then the amount of HA is the amount we start with. I'll call that capital I for initial amount, minus how much reacts, and there's a 1-to-1 ratio between H3O+ and HA. So X amount of HA has reacted. So now we have values for X that we can put in the equilibrium constant expression. So now Ka is equal to H3O+, which is X, A minus, which is X over the initial amount minus X for HA. So this will give us X squared over initial amount minus X. So we know the value of Ka, so we can easily solve for X using the quadratic formula. So let's say we start with a specific initial amount for acetic acid. Say it's 0.01 molar acetic acid solution. So that means initial amount will be 0.01. Okay, so now we'll just solve this for X. So we'll have X squared plus KAX minus KA times 0.01 is equal to 0. When we write the equation in this form, so I'm just taking this denominator over to the left-hand side, multiplying it by KA, and then collecting powers of x. So I can write the quadratic formula because A is equal to 1, B is equal to KA, and C is equal to negative KA times 0.01. So I'll put this in the quadratic formula. Okay, so putting numbers in, I'll have negative Ka plus or minus the square root of Ka squared minus 4 times A, which is 1, times C, which is negative Ka times 0.01, all over 2 times A. A is 1. So I can put my value for Ka in here, 1.8 times 10 to the minus 5th, and you'll notice I have a negative of a negative, so the negative signs will cancel. And I'll get two roots. I'll have negative Ka plus or minus this radical here. Now, the concentration has to be positive, and so we're letting x be the concentration of H3O plus, and so x has to be positive. So we start out with a negative Ka, so that means we're going to have to use the plus root so that this whole thing will become positive, because we have a negative number and we need a bigger positive number to offset that so that we have a positive number as a result. So you know that you're only going to keep the plus root now. You don't have to try both roots and see which one's going to work. Okay, so plugging numbers in for Ka, I'll get my value for x. So x is equal to, so for x, I get 4.2 times 10 to the minus 4. So x is equal to my H3O plus concentration. So now I can find the pH. So the pH is equal to the negative log of the H3O plus concentration. So that's negative log of 4.2 times 10 to the minus 4. And so that gives a pH of 3.4. So this is an example of using a weak acid and using the techniques of equilibrium to determine the pH of the solution.